So in this session, we'll start the design of tension members. So these tension members, normally you'll find them in case of trusses. So what you have is members may be in tension or in compression. So you can have a pure tension member in these trusses. And this design, what we come across in tension member. So it is mainly dependent on three failure criteria. So these are the design criteria, so what have been listed here. So a tension member has to be designed for yield criteria, rupture, and block shear. So we'll see how the strength of the tension member has been expressed under these three different criteria, and these have been mentioned in the clauses of IS 800 2007, that is in section 6, which entirely deals with the design of tension members. So when you start designing the tension member, what you have actually is the factored load given to you, and the length of the tension member will be mentioned. You'll have to fix up the cross-sectional area required, and the shape or the section what you are going to provide has to be fixed. So to find the area required, you can just start with the yield criteria here. So this design strength due to yielding of the gross cross section. So one of the failure criteria, or how the tension member may fail, is due to yielding of the member at the gross cross section. So this is a one criteria which is given over here. So here the strength has been expressed as TDG, the design strength under yielding of a gross cross section. So this is Ag into Fy upon gamma m naught. Ag is the gross cross sectional area without deduction for any bolt holes. So this is the gross cross section multiplied by the yield strength of the material and divided by gamma m naught. Gamma m naught is the factor of safety depending on yield criteria, which we can take it from table 5 of IS 800. So initially, to fix up the cross-sectional area, this particular criteria can help us. So knowing the strength of the member, the factored load, we can arrive at initial cross-sectional area. What is the gross cross-sectional area? What is required over there? So we can use this while designing the tension member, or even while checking the strength of any given member. This equation is applicable. So this is as per the clause 6.2 in page 32 of IS 800. This is one design criteria, yielding. So in addition to this, what we have is the rupture at critical section. So the design strength due to rupture at critical section is given for plates as well as angles. So how they behave, on that basis this will differ. In case of plates, it is 0.9 AN upon gamma m1. So in this, AN is the net cross section. So net cross section will be the cross section what we get after deducting the bolt holes which have been provided in the member. So if it is connected by means of bolts at the ends, so this net cross section has to be calculated by deducting the bolt hole diameter in that particular member. If at all, if it is a welded connection at the ends, then the gross cross section as well as the net cross section will remain the same, because there will be no bolt holes that will be provided within that member at the ends when you use welds as your connections or connecting the member to the gusset plate. So in that case, there is no necessity for deducting any bolt holes. So this is the net area what will be considered here in rupture strength, and Fu is the ultimate tensile strength of the material divided by gamma m1 is the factor of safety based on rupture strength or based on the ultimate strength of the material. This is also available from table 5 in IS 800. So this is for plates TDN. That is how it is calculated. 0.9 ENFU upon gamma M1. When it comes to the angles, so what you find is this is how the angle will be connected to the gusset plate at the ends. That is, one of the legs of the angle will be connected to the gusset plate, whereas another leg we call it as a outstanding leg. This is the connected leg. Here the welds have been used to connect this member with the gusset plate. So this will be the connected leg, and this is the unconnected leg or the outstanding leg of the tension member. So what happens here is there will be a shear lag. So when that force of tension is transferred from a tension member to this gusset plate, this leg will experience a lag while transferring that force. We call it as the shear lag effect. So in order to take account of this shear lag effect, there is a factor beta that has been introduced over here. So how do you find this is given in this equation for angles. This is for angles. For this case, the TDN, the design strength due to rupture at critical section, is given by 0.9 ANC Fu upon gamma m1. This is for the connected leg, 0.9 ANC Fu upon gamma m1. You can observe this is same as the previous equation over here, plus the strength due to the outstanding leg will be beta into Ag naught Fy upon gamma m naught. So this is the design strength due to rupture. So what happens is the connected leg may fail due to rupture at critical section. Once that has failed, or during that, what may happen is the outstanding leg will be experiencing yielding over here. So this is a combination of rupture as well as yielding in the outstanding leg, and taking into account the effect of shear lag by using this beta. Okay, so what is this beta now? So beta depends on several factors here. So beta has been given as 1.4 minus 0.076 into W by T into Fi upon Fu into Bs upon Lc, and you should ensure that beta is less than Fu into gamma m naught by Fi into gamma m1, and it should not be less than zero point 0.7. So two limits have been specified here. Beta should not exceed this particular ratio, and it should not be less than zero point 0.7. So calculating the beta requires you to find these values of W, T, and Bs and Lc. Fi and Fu are the yield and the ultimate strength of the material over here. So coming to this W is the width of the outstanding leg here. So what is the width of this outstanding leg? If it is an equal angle section, then it will be same. Both legs will be of same width. So this width will be W, outstanding leg width. T is the thickness of this angle section. Fi, Fu, as I told it, they are the yield strength and the ultimate strength of the material. And Bs and Lc. So Bs is the connection over here. It is the distance from the connection up to the edge of this outstanding leg, and this is actually taken in this form. So when it is a bolted connection, Bs is given as this width of outstanding leg plus the distance W1. So distance W1 has been measured from this end of the angle up to the center of the bolt hole, W1. Okay, so minus T, W plus W1 minus T. So this is our Bs value. Okay, so this is when you have the bolted connection. In case if it is a welded connection, Bs is directly equal to the width of outstanding leg. So we got that Bs knowing the connection details at the ends. W plus W1 minus T. So what is the edge distance over here? If you know that, or if you arrive at the suitable edge distance in this connection, I can very well find out what is this W1. Okay, so total width of this connected leg minus the edge distance what we provide will give us W1. So W outstanding leg width plus W1 minus T will tell us BS in case of bolted connection. Whereas in case of welded connection, it will be just the width of the outstanding leg. So that is the value of BS in this equation. And LC will be the length of the connection. It will be from the first bolt to the last bolt. The distance from first bolt to the last bolt will be our length of the connection over here. So that is what LC is. So if you know what number of bolts are provided, what is the pitch distance that has been used in this connection, that will give you what is the LC value. So this will be the beta. So when you substitute for these and get the value of beta, compare that with the ratio what has been mentioned here, that is Fa into gamma m naught divided by Fy into gamma m1. So the value what you obtain, it should not exceed this ratio, and at the same time it should not be less than 0.7. So that will give you the beta value. So use that beta value and find what will the design strength under rupture for angles when you are using the angles in your tension member. Okay, so this equation should be used for finding the rupture strength. If it is a plates, then just go ahead with this equation in case of plates. So this is one. There is one more equation that has been mentioned over here, which you will find it in page number 33. That is TDN is equal to alpha into AN into FU upon gamma M1. So this is, if you don't know the exact connection details over there. So this is an approximate equation which can help you to get the value of TDN. It is just approximate. So here what it is done is the shear lag effect has not been considered over here. If at all, if you just want to estimate the design strength under rupture approximately, then you can go ahead with this equation. So here ANFU divided by gamma m naught, that is net area into ultimate tensile strength divided by gamma m naught, and alpha depends on what are the number of bolts that have been used in the connection. So we may just have an idea of how many number of bolts that may come at the end connection. So we can just assume that on that basis we can try with this alpha value if we are just trying to design a member. So in that case you can use this equation for knowing what may be the approximate value of rupture strength. If the connection details are not correctly known to us, then we can try this. So for one or two boards, alpha will be 0.6. For 3 boards, it is 0.7. And for 4 boards and more than 4 boards, it is zero point 0.8. So we can just assume the number of boards that may be coming in the connection, and on that basis we can take the value of alpha and find out what is TDN, rupture strength in this case. So that is one another criteria on which the design of tension members depends, that is the rupture of critical section. And in addition, there is one more criteria, which is the block shear. So block shear, what is this block shear is? In the end connection, so if at all the plate is there, this is how the connection may be. The boards what we provide, it may be in this arrangement, or they may be in one single row also, but this is a case where we come across that block shear when the boards have been arranged in two rows. So what may happen here is, you can see the lines have been numbered as 1 2 2 3 and 3 4. So two horizontal lines are there, these discontinuous lines have been shown, and one vertical line is there. So the failure of plate may occur along these lines. So this is the case what we call it as block shear. You can see the member has failed over here. So this is the due to block shear, failure due to block shear. Another example is here. The tension member has failed due to block shear. And this is a case when weld has been provided in the end connection. So this member has failed due to block shear. This is the member was connected with this earlier. So it has come out over here due to block shear. So how do you find the strength under block shear? So there are two different planes that are involved in here. So one is the shearing plane, this one, two. Another is this tension plane. Perpendicular to the load, you have the tension plane, and parallel to the load, there will be a shearing plane which will be there. So this plane 1, 2, and 3, 4, these two horizontal lines in this figure, they are experiencing shearing, and this line 2, 3, or the area along this line will be experiencing the tension. Same over here. 1, 2, in this member, it will be experiencing shearing. 2, 3, and up to the end of this angle, that will be experiencing tension. So coming to this design strength due to block shear, so it is given as TdB, and we have two separate equations over here. So that will be based on whether the yielding occurs along tension plane or whether the yielding occurs along the shearing plane. On that basis, we have two different equations over here. So first equation, what is here is AVG into Fi divided by root 3 into gamma m naught plus 0.9 ATN into Fu divided by gamma m1. So what has been taken in this equation is yielding is taking place along shearing plane and rupture is taking place along tension plane. You can see AVG. So this is the gross area along the shearing plane. So when I say this gross area, we are not taking into the bolt holes that have been provided along this line 1, 2, and 3, 4. So that will be the AVG value. So this gross area multiplied by the yield strength divided by root 3 into gamma m naught plus 0.9 ATN into Fu upon gamma m1. So ATN is the net area along the tension plane. So the net area can be calculated by deducting the bolt holes. So this will be the center to center distance between this bolts minus the number of bolt holes that we are coming across in this line 2, 3. So what you have is there is half bolt hole what will be encountered at this point, and another half bolt will be coming at this point. So we are only coming across half bolt hole diameter over here. So half over here, half over here, that will be deduction for one bolt hole diameter along this line 2, 3. Okay, so this line, what is the length that we can arrive at by knowing the end or the edge distance what will be provided in the connection. Okay, so once we have this length of the line, deduct for the bolt holes that are coming in this line. Okay, and that length multiplied by the thickness of the angle will give you ATN, the length of the line 2, 3 from center of this bolt hole to the center of this bolt hole minus the bolt holes what are coming in this line into the thickness of the angle will be the area, net area under tension. Okay, so here also I can just you can just refer this diagram over here. BC is the area under tension. If I want to know what is the net area under tension, so this distance, total distance from center of this bolt hole to center of this bolt hole. Okay, so what number of bolt hole diameters we are coming across? So this is the half the bolt hole diameter, okay, at B, and half the bolt hole diameter at C. So total length minus one bolt hole diameter multiplied by whatever the thickness of this member is, that will be ATN. Okay, so I hope you understand how to get that net area. Take care of deduction of bolt hole. What number of bolt holes are coming over there? Total length minus the number of bolt holes. There may be a half bolt hole which you may come across. Okay, so once you find out that net area under tension, that will tell you what is TdB in one of the case when there is a yielding along shearing plane and there is a rupture along tension plane. Okay, then the second is again it is TdB where it is given as zero point 0.9 AVN into Fu upon root 3 gamma m1 plus ATG Fi upon gamma m naught. So if you just observe the difference between the two equations, here it is AVN and Fu. So it is taken that Rupture is taking place along the shearing plane, that is along plane 1, 2 and 3, 4. There is a rupture which is taking place, and the yielding is occurring along this plane 2, 3. So there is a yielding along this tension plane and rupture along the shearing planes. That is what is taken over here. So now ABN, what we require is what is the net area along the shearing plane. So if you take this line from this end of the plate up to the center of this bolt at 2, so this length will be the length of the shearing plane 1 2 up from starting from this end of the plate. So this will be the length in the shearing plane. Such two planes are there, okay, in this particular figure what I am referring here. So ABN will be this length minus one bolt hole diameter over here and half the bolt hole diameter at 2. So that will be the length multiplied by thickness of this plate will give you ABN. Total length deduct for bolt hole diameter, it will be 1.5 bolt holes over here, one bolt hole, half bolt hole over here. So full bolt hole and half of the bolt hole will be there here. We are only taking up to the center of this bolt hole. So this length minus 1.5 bolt holes in that length into the thickness of the plate will give you AVN. Such two planes will be there, so multiplied by 2. In this case, multiplied by 2. Whereas in this case, only one shearing plane is involved here. So this length minus again 1.5 bolt hole multiplied by thickness will give you what is AVN. That will be clear when we take up the problem, but just try to understand what is the AVN, AVG, ATN and ATG over here. So that is net area along shearing plane, and gross area ATG is the gross area along the tension plane. So it will be just the length of this line, that is center of this bolt, from center of this bolt up to the center of this bolt multiplied by the thickness of the member. So we are not making any deduction for bolt holes. It will be gross area along the tension plane ATG. Okay, so these are the different areas what you have to calculate: the net area and the gross area along shearing or along tension plane. So this deduction of bolt holes will be involved only when you provide the bolted connection. If at all, if it is a welded connection, then these net area and gross area they will remain same. The gross area along shearing plane and net area along shearing plane will be same because there will not be any deduction for bolt holes. Then ATG and AVN will also be same. That will be just the length of this line multiplied by the thickness of the member will give ATG, and that will be same in case of AVN also. The length of this line multiplied by the thickness of the angle will tell you what is AVG, and AVN will also be same when welds are used. So you don't have to deduct for any bolt holes in welded connection. Okay, so gross area and net area will remain same. So once you find out this, so you have the design strength under block shear due to two different cases. So least of these two will be taken as the design strength in block shear. Okay, I listed out what how to calculate get the area in different cases over here. Follow these instructions. Okay, so one least of these two will be the taken as design strength under block shear. So now we have three different strengths, that is TD, TD, which is the design strength of the member. We have found one is due to yielding, and we have due to the rupture, and also due to block shear. The least of these three will tell you what is the design strength of the tension member. So least of these three will be taken as design strength of the tension member, and it should be ensured that the factored load what is applied on the tension member is less than design strength what we obtain. So first TDG, TDN and TDB. Out of these three, whichever is least, that will be considered as design strength of the tension member, and compare that with the applied force. Ensure that T is less than TD.